So far we have compared our differences in means and proportions to the value of 0. But we can compare these differences to a different value. And why would we do that? We would do that if the cost of change is positive. So for example, if we find a difference of a certain value, then maybe we need a bigger difference to make it profitable. Okay, so that's why we can penalize our difference with a cutoff value. Okay, so for example, here the cutoff value d naught is 0. So this is what we have used so far. So but if we replace d naught with a different value, then we can actually use that value in our test. So, and it's super easy. We just subtract the cutoff value from the mean, okay, from the difference in means, or the difference in proportions. Okay, so we just subtract this cutoff value, and then we look at how many standard errors this penalized difference is from 0. Okay, so what we can do is that we just subtract this cutoff value. And I think we need to just look at an example, and suppose that moving the first gate from level 40 to level 30 is profitable for Cookie Cats only if the proportion of users who come back to the game after 7 days increase by more than 0.005. Okay, half a percentage point. Okay, what is the null and alternative hypothesis? Okay, so of course we start with the alternative hypothesis, and if this proportion after the change to gate at level 30 is greater than the proportion or player retention rate with gate at level 40 plus the cutoff value. Okay, because now this player retention rate after the change has to be at least as high as the player retention rate before the change plus 0.05. Okay, so this is the cutoff rate, which means that the alternative hypothesis is just the rest of the cases, which means that the player retention rate is equal or below this value. Okay, plus 0.005, which means that these can be written as we need P30 minus P40 minus 0.005 to be less than or equal to 0. Then we make no change. Okay, and the alternative hypothesis is that this sum or difference, I should say, is greater than 0. Okay, and why do we want 0 on this side? Well, it's actually so we can use, let's see, it's actually so we can use this t table and z table. We use the c table when we work with proportions, and this is always centered at 0. Okay, and it's centered at 0 because we can always make a random variable centered at 0 by subtracting a mean. Okay, and we can and this curve is in this table, it's normalized. Okay, and that's because we want to look at how many standard errors we go away from the mean, and then we can calculate probabilities, and we can easily normalize a random variable by subtracting the mean and dividing by the standard error or standard deviation, and then we can use this table which someone else has calculated for us. Okay, it's a bit windy outside, I hope you don't hear it. So that's why we would like to have 0 on the side of this hypothesis test. Okay, that it just enables us to use ordinary statistical tables or formulas. Okay, so that would be the null hypothesis and alternative hypothesis, and if we carry out the test in part I using the 5% significance level, what do you conclude? Okay, so that's when we need to calculate the z-stat. Okay, and how do we do that? We take just the sample proportions and take the difference between the sample proportion after the change minus the sample proportion before the change, but we are kind of penalizing this, and we need to make this difference bigger for it to be economically significant, right? And we just divide by the standard error of this difference. And you see that I don't include the cutoff in the standard error. It's because if you subtract something or add something to a random variable, then the variance and hence the standard error is not affected. Okay, and if we look at this, it's let's see, P30 hat, it's 0.1902, and P40 hat is 0.1820 minus the cutoff 0.005, and divide that by the standard error of this variable or difference, and we have that here, the standard error of P30 hat minus P40 hat is 0.00259, 0.00259, and that would give us a z-stat of 1.235. Okay, and so what we have found is that the penalized difference in proportions is 1.235 standard deviations away from 0. And what we now need is the critical value. Critical value. Okay, so that's just the value from the standard normal distribution centered at 0, and we would like for this tail part to be 5%, because we want to use the 5% significance level, right? And then we can just go to the z table, and here we have the tail probability, and we look here that if we are at 0 here, z value of 0, then the tail distribution here is 0. No, is 0.5, which means 50%, which is logical, because if you cut this distribution at the middle, then the left tail is containing half of the distribution. Okay, so what we do want is for the tail to contain 5%. Okay, 5% of the total area, which means that our cutoff value is 1.64 standard errors away from 0. Okay, and we can use that 1.64, and which means that let's see, from the table, critical value is 1.645. Okay, so this is the critical value we have to use. Okay, and our test is whether or not C statistic is greater than the critical value. And this is false, which means that we fail to reject H0. Okay, so we cannot say that the penalized difference in proportions is different from 0. So that's kind of like a yes or no answer, right? But what if we would like to say that the true value of this difference, the population difference, is within a certain range, okay? And we would like to express to others what the data says about the distribution of the population mean, or the population difference. So then we can look at oh my gosh, confidence intervals. Okay, so the two-sample t-test or z-test determine if the sample mean or proportion is statistically significantly larger in one group or the other. And then, of course, we get like a yes or no answer, but we might want kind of a range where we can, with a certain probability, say that the population parameter is. And how do you make that? Okay, so for example, the two-sample confidence interval for the mean is just the difference, okay, the sample difference, and this you can just plot on the number line. So for example, this sample mean is here, but you would like to know where might the population difference be. Then you have to use the critical value from the t-table, which is dependent on the significance level and on the degrees of freedom. Okay, and it's dependent on the standard error. Okay, the more variation you have in your data, then the larger the confidence interval the confidence interval will be. Okay, so for example, this is, for example, this. Okay, so and this is also subtracted from the sample mean. So now you get like a confidence interval ranging from here to here, right? So, and you can do the same with proportions. So for example, you have proportions here, and here the critical value comes from the normal distribution. Okay, so it's t distribution, and this is z distributed. Okay, normally distributed. So if this 95% confidence interval does not include 0, the difference in means or proportion is statistically significant at the 5% level. So for example, if we have 0 here, then you know that with 95% confidence, your true value for this difference is somewhere in this confidence interval, and if the confidence interval does not include 0, then you're statistically quite certain that the difference in means or proportions is different from 0. Okay, I think we need to just look at an example, and of course we have the cookie cats example. And what is the 95% confidence interval for the difference in the 7-day retention rate, which means the proportion of users who come back to the game 7 days after installation, between the two game versions? Okay, and here we have the difference in proportions. So P30 hat minus P40 hat is 0.1902 minus 0.182, if I remember correctly, which is, let me see, I've forgotten what it was. Yeah, 0.0082. Okay, should have taken that in my head, but yeah, whatever. Okay, and what else do we need? We need the standard error of the difference and this was 0.00259 as we saw, and we need the critical value, okay? And the critical value for the proportion is the z value, okay? The z value. So that would be the z alpha divided by 2, right? So, for example, the z value, we just go to the z test, or z table, I mean, and if we want the 95% confidence interval, okay, if we want a 95% area under the curve, how far away do we have to go from 0 as measured in standard errors? And here we have this area under the curve, and the confidence interval, it's two-sided, okay? So we go both from the mean, we go up and down, okay, just to cover a certain range. So here we have to go up or down, and how far do we have to go to cover 0.95 or 95% of the area? Then here we have the 0.95, and lo and behold, we have to go 1.96 standard errors away from the mean to cover 95% of the area under the normal distribution, okay? So this is 1.96, okay? Which means that we have our expression, which is 0, or confidence interval, is 0.082 plus minus the critical value of 1.96 times the standard error, which is 0.00259, which gives us a range of 0.0031, I think. I'll just have to check, yeah, to 0.0133. So this is the confidence interval, okay? And as you see, it does not contain 0. So and remember that this is the non-penalized difference in proportions. If you would penalize this with 0.0005, then you would just have to subtract that number from the lower end and the higher end of the confidence interval, or just from this this difference, okay? So interpret the 95% confidence interval from part K. So what does this tell us? It actually tells us that with a 95% confidence, we are certain that the true value for this difference in proportions lies within this confidence band, okay? Because if we follow this same strategy and take another sample, random sample, then with a 95% confidence that new sample will also contain, or new confidence interval will also contain the true value of the difference. So we know that 95% of our confidence intervals actually contain the true value if we follow the same procedure. Okay, so that's how confident we would be for each confidence interval we make. Okay, so we are 95% confident that our CI contains the true difference. Yeah. Okay. So, and we can summarize this. And what was our motivation behind the cookie cats example? Okay, it was would, for example, would how could we say this? Would moving the first gate to level 30 increase the retention rate and number of levels played among gamers. Okay, so that's our question. And if this is true, penalized for the implementation cost, of course. If this is true, then we would change. And our method is just like an A/B test. And we used the two sample test, and we had random samples. Okay, and the mechanics of it all was the hypothesis, and the null hypothesis would then be, for example, for proportions, would be the retention rate with gates at level 30 less the retention rate at level 40, less than this cutoff rate. Okay, the cost of implementation, and this should be greater than 0, and the null hypothesis would just be this difference would not be greater than 0. Okay, or it might even be negative. Okay. and then we just make or get like critical value. So this is 1, 2, and then we just make let's see. You get the test value. Okay. Let's see. The Z stat. Sometimes I forget. So then you calculate the T stat or Z stat. Okay. And then for you test statistic versus critical value. Okay, so the message from our cookie cats example is that we could not tell if there was a difference in means because the sample size condition did not hold. Okay, sample size condition did not hold, and that was for means. And for proportions, the difference in proportions, including the cutoff, was not greater than 0, statistically speaking. Okay, so difference in we just do this difference not greater than 0, including D naught. Okay, see you next time.